talking about waveguides last time, and what I want to do is I'm going to go through this into the TE and TM versions, and I'm going to show you the important characteristics of waveguides. I brought down a couple little examples of waveguides last time. I want to say this: there are cylindrical waveguides. We don't go through the mathematics of waveguide propagation in cylinders because the solution requires Bessel functions. And have you had Bessel functions yet in your differential equations course or anything? I mean, most of the solutions that you see for a wave equation are going to be in terms of sines and cosines or exponentials, e to the plus or minus j beta something. But a cylindrical waveguide, the solution for the del squared operator on that will render something called Bessel functions. And you haven't heard. Well, anyway, we don't cover it here, but I'm just letting you know that there are cylindrical waveguides, and they're fairly well understood. Actually, that looks a little dark. So, we were talking about propagation, we were talking about the TM modes right here. And the TM modes that mean that HZ is equal to 0. There's no H field in the direction of propagation. So again, for the waveguide itself is just a rectangular tube like such. They're conducting surfaces that has a horizontal width of A, vertical height of D, and A is always greater than 2B. And the wave propagates in this direction, the Z direction. So normally this is called X, this is Y, and this is Z. I'm just talking in generalities here because I want to just key your mind up. That's where we left off. So now when we looked at the rectangular waveguide cross section, and call that X, call that Y, and this be the origin. Again, the width of this is A, and the height of it is B, and these walls are considered perfect conductors. So we go ahead and we solve the wave equation. Last time we started out, we had, remember I came down, I had del squared of EZ plus, and then it was omega squared mu epsilon times EZ equals 0. Do y'all remember? I was about there. Do y'all remember how I got there? All right, the way I got there was I started with the two Maxwell's equations and I derived a single equation with a single unknown. And now we're looking at only the EZ component of this. Some of this is going to kind of make you think there's so much material right here, but I'm trying to cut down to the essence of it. So from there, we had to use something we had called separation of variables. This is where I was last time. I'm trying to just bring us up to speed. And I said with separation of variables, we can assume that EZ is just a function of X times just a function of Y times just a function of Z. And you've had this in your differential equations course. So if we have that, and right here, look at what we got here, and the next step is we're going to take the del squared operator and turn it into single derivative. So this becomes second derivative of EZ with respect to X squared plus second derivative of EZ with respect to Y squared plus second derivative of EZ with respect to Z squared plus, and then we'll substitute beta unguided squared here for omega squared mu epsilon times EZ equals 0. And I'll make a notation. In Dr. Wentworth's book, he uses a beta sub u, and that's equal to omega square root of mu epsilon. The mu and epsilon are inside this rectangular tube. Whatever they are, usually it's air, so it's usually just mu naught epsilon naught. And omega is the frequency 2 pi f. Okay, so we're there, and now when we put this, it's an assumed solution. We're assuming we can do this. If we can't, it'll be evident when we actually do the derivatives. Then you'll see that you can't get a separation. When you do this, you get X double prime times YZ plus X times Y double prime times Z plus X times Y times Z double prime plus beta unguided squared times X, Y, Z equals 0. That's where I was last time, I think. And now, remember, for derivatives, the double derivative right here, on x I just put 2 little apostrophes. Y'all with me on this class? You're familiar with this notation, right? Derivatives could be an apostrophe, or they could actually be shown as dv. So then I divide everything here by x, y, and z. So when we divide everything by x, y, and z, then what you see, we get x, and this is the important part, x double prime over x plus y double prime over y plus z double prime over z plus beta unguided squared equals 0. That's the important part. Now again, the only thing I'm doing is I'm manipulating this equation to get it into something I can actually get solutions for that are meaningful. That's the whole point. This is in the chapter. Now remember, x is only a function of x. So I've got double derivative of x, whatever the function is, divided by x, plus a function of just y, plus a function of just z, plus a function, plus some constant, beta mu squared equals 0. The only way this can occur for all values of x, y, and z is if these are constants. They have to be mathematically a constant. All right, that's the key. And what we do is we call the x double prime over x simply, now I like to use kx. Dr. Wentworth puts it, he'll put it beta x squared, and he'll put a negative sign there. For here, he'll put minus beta y squared. And then in Wentworth's book, he won't put beta z. I do, and I'll explain why. This is minus beta z squared plus beta unguided squared equals 0. Okay, just pull that dot. So that means that x double prime over x is equal to minus beta x squared. Y'all follow me? And that's a constant. We don't know what it is yet, but that's got to be a single constant value. We put the minus sign there. We don't have to, but we're going to find if we don't, we end up getting an imaginary value for that beta. That's the reason we put it there. So when I manipulate this, I'm going to get x double prime, all right, plus beta x squared times x equals 0. And if you look at that, that's the second derivative of x with respect to x squared plus beta x squared times x equals 0. And again, now I've just expressed the double primes in terms of the actual derivative. Now that's a second order homogeneous differential equation. I mean, do you remember solving this back in the day? How would you solve it? There's a couple ways. You could use what? Integration factors. And you could use what? Laplace transforms. Do you all remember Laplace transforms? You can do it a lot of ways. Matter of fact, it's a very straightforward thing. I can take this to the other side, and then I can introduce an integration factor. I can assume a solution. That's the way they taught you in mathematics, that you assume, because it's a linear differential equation, the solutions will be of the form a e to the gamma x. Do you all remember that? And then you just literally put it in there, did the derivative on that, and solve for what gamma is in terms of the constants. How many remember doing that? One? Well, y'all have been exposed to it, whether you recall it at 8 in the morning or not, you have been exposed to it. So, I mean, here's what I'm talking about. They'll say, we're going to assume the solutions. Let's say x here is going to be assumed to be a e to the gamma x. This is an assumed solution. We don't know if it's going to work, but it will work because it's a linear differential equation. And that exponential operator always works. I stick it in there, I get two derivatives, so I get a gamma squared here times the function x. Because remember, if I take one derivative of this, I get gamma, right? Two derivatives, I get gamma squared, right? In front, see this with respect to x? Then I just get the function itself. As a matter of fact, I don't need that big. I get this. I get this plus beta x squared x equals 0. And the only way this can happen is if gamma squared plus beta x squared equals 0. Y'all see that? Can you all follow me on that? I just factored out the functional form x, and you get gamma squared plus beta x squared equals 0, correct? Remember doing this now, kind of? Now what does that mean? That means gamma squared, right? Well, you can do it this way, you can factor it. You can get alpha minus beta x times, let's see. Actually, what I should know is this. I should assume the minus there, and that would make, well, no, I can do it that way. So then you're going to get lambda is equal to plus or minus j times square root of beta x, actually square root of beta x squared, which is just going to be equal to gamma is equal to plus or minus j beta x. And anyway, make a long story short, that x would be the solution to that. I end up getting the functional form for x can be either, by the way, because of the nature of this could be a sine, cosine, or it could be a strict exponential decay. This can have some form of some constant a times the cosine of beta x times x, or it can have a form of constant times the sine of beta x times x. These are the possible solutions, or it can have the form a equal to plus or minus j beta x times x. That's the possible solutions to that differential equation. Whether you recall doing this stuff or not, it's in Dr. Moore's book. He talks about it. You can do it with Laplace transforms easily. But if I come down to this, remember sine and cosine are just what? Sums of exponentials, aren't they? A cosine is e to the j times the argument theta plus e to the minus j argument of theta over 2. Do you all remember these Euler's identities? All right, so these are still exponentials. They're sums of exponentials. Now, when I look at this, and I look at this here, and I'm going to try to really make a point here. Remember, dimensionally, this is a perfect conductor. That's 0. This is the x dimension. This is A. This is 0. This is the y dimension, B. And my solution here for x is a component of the solution for EZ. It's one of these three functions, right? So when you look at that, here's the important thing. We know that that function, x, has to be 0. Remember, EZ is in the direction, it's if you think about this, EZ is going to be the component of the E field that's parallel with these boundaries. Do you all see this, class? In other words, EZ at the boundary has to be 0. So if we look and we know that this functional form of x has to go to 0 at the boundaries, at all these boundaries. Just take a look at that. It's got to be 0 when x equals 0. It's got to be 0 when y equals 0. It's got to be 0 when x equals a. And a cosine won't do that. You all see if you plug in a value for x equals 0, that a cosine of 0 is 1, right? The only way for a cosine to work is if a is 0, then you don't have a solution. You have the null solution. So it has to be a sine. That means the x functional form will be some constant a times the sine of beta x times x. That's going to be the functional form. That checks the box when x equals 0, that solution is 0, correct, class? Now, where else is this going to be 0? Well, please follow me. It's also got, EZ has got to be 0, which means the functional form of x has to be 0 when x equals a, right? That's the other edge. Follow me on that? So the only way for this solution to work here is if the sine of beta x or sine of beta a of beta x times the dimension a is equal to 0. You follow my rationale on that? It takes a little time to get your head around this, but you can do this, trust me. You just, first you got to just accept it and then work through it on your own. Now, when is a sine equal to 0? What arguments of a sine make it 0? If I just put this, say you're going for a job interview. They want to know what theta equals. Well, sine is 0 when theta is 0, right? We checked that box earlier. When else is it 0? Think about it. Or it's pi, right? 2 pi at minus pi at minus 2 pi, right? As a matter of fact, what we can say is when beta x, the argument beta x times a is equal to m pi plus or minus m pi, that's a solution. That guarantees that the sine function goes to 0, right? And now we can see what beta x is. Beta x here will be equal to, and we just ignore the negatives in this one, are going to be simply m pi over a. We don't need negatives. So that's the possible value. That's all the values that will work for the solution for beta x. We've checked the box. We know what beta x is. Okay? And it's a function of m. M is an integer, so m could be 0. That would be the null solution. M could be 1. M could be 2. M could be 3, and so forth. And we're going to see what that really does is it tells us the allowable propagation modes. When m is equal to 1, you get this as far as the taper on the magnitude of x. When m equals 2, you get this, and so forth. Just go with me on this for now. But it tells me the form of the function for different values of m. There's a lot coming your way on this. Now, next. I'll leave that there. Next part I'm going to do is this part for y. So it's going to be the same exact thing as the x I have. Y double prime, when I do the separation, I get the second derivative of y with respect to y squared plus beta y squared times y equals 0. That's just this equation right here. Y'all follow me? If I take this, I set y double prime over y equal to minus beta y squared, then multiply both sides by y, and then pull over the minus beta y squared times y on one side, set equal to 0, I get this. That again is a simple first order linear differential equation. It's homogeneous differential equation, okay? And again, there's so many different, by the way, one of the things you may see in a job interview by yourselves, when these days you go to companies and, you know, degrees sometimes don't represent your real level of skill in terms of your GPA and stuff like that. So they give you tests, they do all the time nowadays. And you may see a differential equation written by somebody and they say, can you solve this for me? And it's important at least you have enough confidence to solve something like this without a lot of hesitation and gasping for air. So I'm just telling you the facts. Has anybody ever gone for a job interview and had one of these tests?
Not this one.
Well,
other tests, not this.
when you go for a job interview and you got a bachelor's degree in engineering and you go to like Intel, you can have a very high GPA. Matter of fact, usually what they do is a lot of companies like Google, they won't even look at you unless you got about 3.8 or 3.9, no matter where you're from, including MIT. All right, but once you get in the door, they don't assume you know what you're doing because I guess since COVID and probably even before then, there's a lot of people that they cherry pick courses to get a high GPA. And the people out there know this, so they're going to give you these quizzes. And if you can't do this basic stuff, it's basically, well, thank you, and goodbye, because they want to make sure that they're getting what they think they're getting, because they're going to be paying you a lot of money. All right, for that one, the general form of the solution will be also that y will be equal to possibly a times cosine of beta y times y, or it could be a times sine of beta y times y, or it could be a times e to the plus or minus j beta y times y. Either one of these. Now, again, you always go to the boundary conditions. That value of y there is part of this assumed solution, and it represents EZ. Got me on this? Now, we know that EZ has to be 0 on all these edges. Y'all follow me on that? It has to go to 0 because that's a perfect conductor, and that is tangent to the conductor, right? EZ has to be, y'all know, when you have a perfect conductor, the electric field in the plane of that conductor has to be zero, right? You can have a normal electric field, but the tangent component has to be zero. Do you all remember this class? It shorts it out. So the only way for this to be zero is, think about it, it's got to be zero when y equals zero. That's this portion here, right? Y equals zero is that. Well, when y is zero, the cosine goes to 1, right? Cosine of 0 would be 1. That will not work. It just doesn't work. But the sine does. You all see when y is 0, it checks that box. So this one is going to work. This will never go to 0. So that's not allowed either. This is a propagational mode. This is the only one that works, and it has to be 0 not only at y equals 0, that's here, this is the y dimension, but it has to be 0 when y is b. Do you all see that, class? That's the upper portion. All right. So when we take a look at this, it means that a times the sine of beta y times b equals 0. And again, this is just replicating what we did a second ago. So when is the sine 0? The sine of the angle theta 0, the argument? When the argument is 0, right? Or m pi, plus or minus m pi, or n pi in this case. It's going to be a different integer. So that means that beta y times b has got to be equal to, and we use the letter n pi, and it's going to be plus or minus, but we're going to just stick with the positives because the negatives lose any kind of meaning. So that means beta y is equal to n pi over b. Now we've got the x and y, capital X and capital Y solutions. Both are sine. Y'all with me? All right, now this is one of the things I differ with Wentworth on this. Dr. Wentworth's book, he doesn't put minus beta z there. He calls this beta. And the reason he calls it, I don't like this, the reason he calls it beta because that is the actual beta that has to do with wave propagation in the z direction inside the guide. He labels this beta unguided because it has to do with wave propagation in unguided or free space. If there was nothing confining the wave, that tube literally causes the wave to just ricochet back and forth. So we come over here, and when I look at the z mode, and let me do it right here. Now I get this. I get the second derivative of z with respect to z squared plus beta z squared times z equals 0. And for that one, when I look at this, the solutions for these that will work. Remember, this is going to be something where, now when I look in the z direction, and I think about this, this doesn't really have any zeros in terms of, except on the very edges, but they're guaranteed to go to 0 because of x and y going to 0 on the edges. This is the propagation modes. And the allowable modes are some constant a, e to the j, beta z times z, and a, e to the minus j of beta z times z. Now this is a wave propagating in the negative z direction. This is a wave propagating in the positive z direction. Y'all with me on this, class? Those are allowable. Usually we just look at the positive z propagation because that's the only thing that is of importance to us. Now what we have is the general form of the function. When I look at ez and I say it's equal to x times y times z, that means it's one constant. And the constant that Dr. Wentworth uses is E0 times the sine of, and this would be beta x times x. Beta x was equal to m pi over a times x. Then it's times the sine of n pi over b times y. And then it's going to be e to the minus j. And it's going to be beta z, but we're gonna have to get this in a second, times z. And this is actually in Whitworth's book, he uses just the symbol beta for this. Not beta z, but I like beta z because it distinguishes it very clearly from beta unguided. Right, now, how do we get beta z? Because that's the last one. Let me do you a favor too. I'll tell you where this is in the book, so you won't, I mean, there's gonna be some head scratching with this stuff the first time I go over it, I know that. All right, we're going, this is page 388 is where it starts. And he only assumes the solution x, y should be x, y, and z. And now, what I'm about to do is down at the bottom of page 388, but again, I use beta z also. And remember, his beta is my beta z. So now I come down here, and you see this equation right here? Now what I'm gonna do is, I'm gonna put in the values we got for beta x, beta y, beta z, and I'll put beta unguided as omega squared times mu epsilon in there. So I have minus beta x, or I have minus, and this is gonna be m pi over a squared, minus beta y, n pi over b squared, minus beta z that we don't know yet squared, and then plus omega squared times square root of mu, or omega squared times mu epsilon, okay, equals 0. Right. That's just sticking in the values of beta we found into this equation. Follow me? If you've got, somebody's got your books there, you can take a look in his book, what he has. And I'm about to do this. The very bottom of the page, right there. Right there. That's it right there, and we're gonna get to that in a second. That is beta c, bottom page, 389. So we're working through this. All right. Now, to get beta z, I'm simply gonna take this to that side and mess with this a little. So I see that beta z here squared is equal to omega squared here times mu epsilon minus n, or m pi over a squared minus n pi over b squared equals 0. And that in fact is beta z, that's absolutely correct. Now, something very important has to be discussed. Well, that is the solution. You can see that beta z itself would be equal to the square root of this. Y'all agree? All right. Now, and it would be plus or minus this too, plus or minus the square root. There's a very important thing that happens with this equation that we have to talk about. When I look at this, you remember how I said that for both the x and y modes, the allowable solutions, they have to have a 0 here and a 0 here, right? Now, if you think about that for a second, if beta x was too small, I couldn't get away with it. In other words, it wouldn't change fast enough. If I had something where it went here to 0, not here, that wouldn't be allowable solution. So what actually happens here is we have something called cutoff frequency. And the cutoff frequency is the frequency, or this is the minimum frequency needed for wave propagation well, let me explain this the best way I can. I'm trying to just do this in a way that will make sense to you. So I've got this metal tube, and somehow I'm exciting electromagnetic energy. Usually they cut a little hole in here, and they're gonna put a small antenna down here, and they're gonna drive a current in that antenna, and this antenna, what it does is it's gonna have a certain frequency, but it is the thing that initiates the electric field behavior in here. It basically is gonna start the actual motor running in this thing. And I hate to say it that way, but this is how they do it. They put a small little antenna in, and that's how they feed waveguides. I'll spend more time on that later when we get into antennas. Now, the waveguide itself is a high frequency filter, or really it stops low frequencies. And here's what I mean by that. If you have this waveguide and you try to propagate a mode at a frequency that is below this cutoff frequency that we're about to discover, it won't propagate, it'll just short out in the wall. And the reason it shorts out is because the wave itself will try to fit the form of the solution to the del squared operator, and it'll try to have a half wavelength this way, at least. But it can't, it's too long. The frequency is too small, small, and it won't fit. So the waveguide is a high frequency filter. Some of this you'll appreciate in a little bit. And where does this cutoff frequency happen? It happens when beta Z is 0, okay? Write that down. So this cutoff frequency occurs when beta Z equals 0. Now, when is beta Z 0? We're gonna see in 1 second. Well, if you look at this, for beta Z to be 0, that means this is 0, right? Which means omega squared mu epsilon is equal to this other side. Y'all follow me on this? Just watch. If I say beta Z equals 0, it means omega squared mu epsilon is equal to m pi over a squared plus n pi over b squared. Can y'all follow me on why that's true? Because the argument inside here has to be 0. It means this side has to equal this side in magnitude. Y'all with me? Okay. Now, this frequency, we call it omega cutoff, is 2 pi f cutoff frequency. When you take a look at this, just follow me on this. I'm going to go ahead and first thing I'm going to do is take I'll take omega, replace it by that, so I have 2 pi times f cutoff squared times mu epsilon is equal to m pi over a squared plus n pi over b squared. Now y'all follow me, the only thing I've done is replaced omega with 2 pi f, and I put a c there to indicate this is the cutoff frequency. With me? Now, can you all see I can get rid of the pi's everywhere? Just take a look at that. I got a pi squared there, pi squared there, pi squared there. Divide both sides by pi. It goes away. So I get this. Okay. Now, if I manipulate this, I can take the square root of both sides. Do y'all agree with that? So I'm going to take the square root of everything here and here. And that means I have 2 times the square root of mu epsilon times fc is equal to the square root of m over a squared plus n over b squared. Or I can put it, the cutoff frequency, and this is the one you put down, the cutoff frequency is equal to 1 over 2 square root of mu epsilon times square root of m over a squared plus n over b squared. And this is the cutoff frequency for a rectangular waveguide. Now, for any given m and n, I can get you the cutoff frequency. So the cutoff frequency is actually a function of m and n. Y'all follow me on this? I know it's a lot to swallow this early in the morning, but you're going to have to just appreciate this. These are the cutoff frequencies. Now, getting back to this thing over here. where this is beta Z. And take a look at those cutoff frequencies. What I can now do is manipulate this thing, and I think in his book, I'm not sure how he shows this, but I don't know if he does it in Omega. What I've just got there is on the bottom of page 389, and then if you go through 390, he doesn't even do the proof on it. I'll just do it where he does it. So now he says, what actually is happening here is now we have EZ given as really some constant E naught, E times the sine of M pi over A times X times the sine of N pi over B times Y times E to the minus J beta. And he just leaves it beta, but I put beta Z on it because mine's always beta Z. And this is beta Z, but now I can manipulate that further to get the actual value of beta Z in terms of the cutoff frequency. And I think, I'm just trying to find out where he has that book. So I can give it to you as a reference. So this is the cutoff frequency. And now if you take a look at this, I mean, I could do the cutoff frequency a couple of different ways. Let's see. If I put that times 2 pi, I want to do something here, just bear with me. I'm going to say omega cutoff, same as this, is really going to be 2 pi times that. So it's going to be pi over square root of mu epsilon times square root of M over A squared plus N over B squared. That's omega cutoff. And if I do that, then what I can do, I'm going to go right there. I want you to write this down too. Try to understand something. When I look at this equation, let me try to get better than this. I'm going to go ahead and bring the pi operator inside here for a reason. That's omega cutoff. And then I'm going to take square root of mu epsilon over here. So I'm square root of mu epsilon times omega cutoff is equal to the square root of pi times M over A squared plus pi N over B squared. Here's what I'm up to. I'm doing that so I can take this right here, which is equal to minus, and I can do the quantity of this. Y'all see how this right here, well, it's the square root of that, so if I square both sides, if I square both sides, then I get omega c squared times mu epsilon. Y'all follow me on this, class? I'm trying to get this portion so you can see it exactly. Now, if I know that this is the cutoff frequency, it's simply 2 pi f cutoff, this defines the cutoff times mu epsilon, is that. And now what I can do is divide, if you take a look at this, or pull out, however you want to think about it. If I go ahead and I factor that out of this, I end up getting omega times square root of mu epsilon, just bear with me, and it's gonna be square root of 1 minus f c over f squared. And this is beta z, now star that. In Whitmer's book, he doesn't show you this clearly, but I'm trying to, well, maybe he does later, but this is real important. Now that cutoff frequency there is a function of m and n, and there'll be different cutoff frequencies squared. And now what you can say is this is basically beta unguided, or you can write this down. Beta z, which is Wentworth's beta, is really equal to beta unguided, or just omega times square root of mu epsilon times the square root of 1 minus fc, and it's gotta be the mn mode of that, over f squared. And this is beta z. And it should be in Dr. Whitmer's book somewhere, maybe in the next sections. But that's how you get the beta z that goes right here. Now, the thing about this is, f here has to be greater than fc for propagation. Just take a second, catch your breath on this one. Here we go. Try to make sense of this. Okay, when you look at this, this fc right here has to be greater, or I'm sorry, f has to be greater than fc, makes this less than 1. Do y'all see that here? All right, 1 minus something less than 1 is still positive. Now, if fc, or if f was less than fc, then what would happen is this would be greater than 1, and I'd get the square root of minus something, which is plus or minus j something. Are y'all with me on that? That's not a propagating mode. So for propagation, f has to be greater than fc. I'll put it here. Where you got this? F has to be greater than fc. Now, last thing about this. If you look at this right here, remember, this, we can get beta z now, we can calculate the cutoff frequencies for any value of m and n, but this is real important. When you look at this, just think about it. What if both m and n are 0? Or either of them are 0? What happens if m is 0? What do you get? The sign of 0, which is 0.
Oh, yeah.
Sign of 0 is 0, right? So if either m or n, these are the mode numbers they're called, I'm just telling you, there's a lot of stuff coming at you. M or n are 0, nothing propagates. Y'all with me? It means the lowest order mode, I'll write this down, the lowest, they call it order mode in TM propagation is when m equals 1 and n equals 1. Both have to be at least 1, or else this is a null solution. Nothing propagates for the TM mode. We'll see later that for the TE mode, you can have a 1, 0 or 0, 1, but you can't have a 0, 0 mode. But this is for TM propagation. So that means the cutoff frequency for the 1, 1 mode will be equal to, and it's over here, right here, 1 over 2 square root of mu epsilon times square root of 1 over a squared plus 1 over b squared. That's the lowest order mode, and you have to be above that frequency for propagation to occur in a TM mode. Okay, just trying to get everything out of it. Now, in his book, if you have it.
Real quick, I think I kind of lost you where you factored in the 1 over FC, or 1 minus FC over F.
The only thing I'm doing is I take this right here, and I divide everything. Here's what I'm going to do. I'm going to factor this omega squared mu epsilon outside. So when I do that, I get omega here, mu epsilon. That's this, all right?
Yeah.
Then, what I end up with is 1 there, right? Because if I factor that, I get a 1, minus, and then this is the omega C mu epsilon. It's this, and if I, because I've got that there already, I divide it by, then divide it by, F, and I get this right here. I mean, it's gonna be actually gonna have, omega squared mu epsilon, you divide it by. So the 2 pi's and all that stuff, and the mu and epsilon cancel, and you're just left with F down there squared. That's how I got it. Sorry if I didn't.
I might have been writing something when you said it.
Wow, it's easy to miss this stuff. So that's the lowest order mode for the TM. And box that, and this is lowest order mode. This just means this is the minimum frequency that will propagate in TM mode. All right, now, in your book, since we have EZ, I'm just gonna cut to the chase on this. I'm gonna erase this, because I need some more board space. I'm gonna leave that there. I've got EZ for the TMO. It's a mathematical solution. Now, how do I get the other components? And I tell you, the way it always works is, if you got one, you can get the others by doing this. Remember, we know that HZ is 0, right? That's absolutely true for TMO propagation. That's an assumption, but it has to be true, or else you can't have TMO propagation. Now, when you take the curl of E, you end up with minus J omega mu times H. Y'all follow me? I know that EZ, we have just the Z component, but what we can do is go through the curl equations, and this takes some time, so I'm not gonna do it right now, but some of this is in your book. If I take the curl operator, right, I write the curl for E in general, and I'm gonna get a curl of E, and that will be, when you do it, I don't wanna do this, but I'll show you. It would be AX, AY, AZ, DDX, DDY, DDZ, and that's gonna be EX, EY, EZ. That's a determinant of that is equal to curl of E. Y'all with me on this much? Now look, we've got this one, right? We just got it. So if I come down here, I have AX, DDY, EZ, minus, and then it's going to be minus DDX of EZ, and it would be the AY component. Now I'm going to get partial, you might say a partial curl equations, but because HC is 0, when you go and do the math on this, all the different values for both EX, EY, HX, and HY can be gotten, but it does take some time. And he shows us on page 390. You are not responsible for memorizing all this. I'm going to just tell you that. You just have to be aware of how you get it. You start with that solution there, do the curl, and then start equating things. And you'll see when you do this, you'll get EZ, and you'll get EY, you'll get EX, and you'll get HX and HY. And he has the solutions there. And this is for TEM mode propagation. Now, I gotta tell you the one thing that's important, because this is a lot. That is important right there. And then there's one other thing. I'm not gonna do this. This takes some time, but it's doable, and it'll get you all the electric field components, and he has them. But here's one thing that is important. When I take a look at the ratio, this is for TM propagation. The ratio of EX to HY, or the ratio of EY to HX, you'll notice they're perpendicular to each other. XY, YX, both the E field and H field are perpendicular. They're not EX to EY. Y'all follow me on this? And he shows this in his book, what I'm about to show you. And this is at, on its equation 7.54. But when you do that, you'll find out you get a ratio of beta over omega epsilon. And really, this is the key thing. Write this down. This is called the impedance, the characteristic impedance of the waveguide in the TM mode. So ZTM is the characteristic impedance. Now, this is just like, you know how in a transmission line you had a characteristic impedance of the transmission line? Same exact thing, but this is the characteristic impedance of the waveguide. And what it actually equals, ZTM, and this is the one you write down, is equal to eta of the waveguide, and maybe I should do it this way. It's equal to the square root of mu over epsilon, that's inside the guide. And then it's times simply the square root of 1 minus FC over F squared. That gives you the ratio of E to H. Now you'll notice one thing. When the cutoff frequency, when F is the cutoff frequency, the characteristic impedance is 0. Can you see that? If FC and F are the same, you got 1 minus 1 is 0. It goes to 0. So if you were to actually plot this, and this is important, and they do this, if you had this versus frequency, and this is the cutoff frequency, and this is going to be the magnitude of ZTM, actually, just can call it ZTM. It does this, it starts at 0, and asymptotically approaches the characteristic impedance of free space, which this would be eta, or I should say in the guide, eta here, and eta is really the square root of mu over epsilon, and in free space it's 377 ohms. Now this is important. So the lower in frequency you get, the ratio of E to H is dropping E perpendicular to H perpendicular in the not in the Z direction, but in the plane of perpendicular to the plane of propagation. It's going to go to 0. So in summary for the TM modes, the key thing is cutoff frequency, understanding this is the form for EZ, and it can be for MN equals anything 1 or greater. That is the characteristic impedance. Now, a bit more interpretation what all this means, because there's a lot of math coming at you that you really don't appreciate yet. I know this. So what does all this really mean in terms of understanding what's going on? So I have a waveguide, and I know it's a high frequency, high pass filter. It's got to have a certain minimal frequency for TM modes to pass. I figured out what that is over there. Then I also got this impedance business over here. And what's really going on inside the guide? Let me try to explain this. Here's my cross section, my guide. If you have M equals 1, N equals 1, in that mode right there, and propagation is occurring, here's what's really happening. I know that the E field for 1, 1, the value of M equals 1, it means the variation of the E field in the Z direction versus X has a sine wave form. And what'll happen is this. You'll get a half wavelength here. This is going to be, I'm trying to represent the sine of pi over A times X, where this would be X. You all see you would have a sine waveform there, right? This is going to be a half wavelength. This is lambda over 2. And I'll get into that more and more. Matter of fact, let me just put it this way for now. That's the actual graph of this, the 1, 1 mode. If you look at the vertical direction and the layout for the sine of pi over b times y, it does this. Try to appreciate it's a half wavelength at cutoff. So at cutoff frequency, you would have a variation in E field this way, a variation in E field this way versus vertical. What would actually happen is, at the end of the day, if you looked at the actual magnitude of EZ, and you drew contours of equal potential, and he does this in the book, you'll get this. For the TM11 mode, you basically get this. You're going to get contours that look like this. They're basically circular, where these contours would have a very large value in the center, and asymptotically they're going to zero. I'm trying to show you contours of the magnitude of EZ. And he does this, if you look on page 392 in your book, just write that down. He has contours, and he tries to show you what EZ would look like for the different modes. Now, for the 1-1 mode, it means there's a large electric field right in the center, but it asymptotically goes to zero. It's hard to appreciate this, I know, but you're gonna have to just try. Now, if it was the 1-2 mode, or, and I'm trying to take this and say, well, if the variation in height is proportional to the sine and versus the horizontal distance is sine, and there's exactly a half wavelength there, I call it half wavelength. Then if we multiply the two solutions together, you would get contours that would look like this. Contours just equal magnitude. And they would go to zero at the edges. If it was the 1 or the 2-1 mode, yeah, 2-1 mode, then you get this. And he shows you this. I wish I could explain this a little better, but it's very hard because the terms I would use are not, you're not familiar with. So if it's the 2-1 mode, then I'll get the variation in x of the solution would look like this. Remember, this is over a distance a. That means here there would be a 2, not a 1. And here there would still be a sine variation vertically, all right? Now just try to do this math in your head. If you're saying that I gotta multiply a sine variation this way, where it's half wavelength, versus another sine in that direction where it's a full wavelength, then you can see right at the center you get a null. Can you see how there's a null right there? All the values up and down there are null. And what you'll actually get in terms of equal potentials then, surfaces, if you just take this, you're gonna have now two centers where you're gonna get equal potentials. I mean, the circles will look like that. They won't look like a big one where it's gonna have a zero right there. Okay, just try to appreciate this. There's a lot happening here. And he shows you that in, well, maybe he doesn't show you that. Let me try. Huh?
So yeah, I noticed the same.
I guess what I really should show you, if you look on 394 at the top, that's the easy field for the 1-1 mode. But for the 2-1 mode, you would have, the easy would have a concentration here and here. You're gonna have to just take my word for it, it's true. And I'm sorry that some of this stuff is very hard in the mind to appreciate. What he's really just showing you is how the electric field structure would actually be developed for the different modes. Now, something I gotta tell you too. When you actually have a waveguide and you energize it with an antenna, it has a given frequency, that waveguide has to allow modes to appear. Let me try to make a mechanical analogy to this. You all know what bells are, right? Think of a large bell. When you hit it with a hammer, it rings at a certain frequency, right? Called the resonant frequency, right? All right. With a waveguide, as you're driving it with a given frequency, the patterns developed are similar to resonance. They're the allowable propagation patterns that will allow the wave to move down the guide. And they're constrained by the mathematics that we were talking about earlier. So, and if you have a frequency, and I'll try to say, if I have a frequency that's just over the 1-1 frequency, then I'll develop the 1-1 mode as the field pattern. Do y'all follow me? We're gonna get the velocity and all that in a second. As I keep increasing frequency, when the frequency is above the 2-1 mode, follow me? That would be the next lowest mode. Now, both the 1-1 and the 2-1 mode will be developed. Do you all follow me? You're going to have electric fields that will configure themselves like the 2-1 if the frequency is above the 2-1 mode, and like the 1-1 mode. And then a good question is, how do you figure out how much of the field or how much of the power is in the 1-0 mode or 1-1 mode versus the 2-1? That's another much more difficult problem. As a matter of fact, that's like doctoral level stuff. And here's something, and you're going to see this. When we propagate, use a rectangular waveguide for any type of energy communication, either a microwave link or anything like that, we do it in a way so that only one mode will propagate. All right, and that guarantees that the frequency of propagation will also be, it will not vary. If you have two modes, there's two different propagational frequencies, and it's a mess because then everything gets really, what you end up getting is garbled stuff. There's not coherency. I'll try to explain this a little better in a second. Keep that in mind. We're going to go on to, while I'm still here, let me just show you what the velocity of propagation would be. Remember, we're still talking about TM, but what I'm about to show you is true for all propagations, or at all modes, be TE or TM. So, well, what is velocity of propagation generally? Do you remember?
Can I go
For,
to bed?
yeah,
One, two.
you're right. Velocity of propagation is one. How do we get that? Remember, you took the argument of the cosine function, and you said that you want to take a derivative of that argument, which is omega t minus beta z, and set it equal to 0, right? And you end up getting omega over beta, all right? But now this beta is beta z. So now I have omega here over beta z. And remember, beta z, I did this on purpose. I said, well, beta z can be represented as just beta unguided, or as omega times square root of u epsilon, right? Times the square root of 1 minus fc over f squared. Do you remember I put that down for you? I put what beta z was, and I couldn't find it in one more book. Now, if you look at that, you'll notice one thing. The omegas here get canceled. Y'all follow me? They get canceled. And I'm left with 1 over the square root of mu epsilon divided by 1 over the square root of 1 minus fc over f squared. We introduce another constant usually here. We call k equal to the square root of 1 minus fc over f squared. But that means the velocity of propagation right here will be equal to 1 over the square root of mu epsilon divided by 1 over k. Now just write that down, and here's what you have to appreciate. Because I know so much is coming at you. And at 8 a.m., this is going to seem pretty abstract, but I'll try to make sense of it. Now, if you look at what happens to this when you have cutoff frequency, just take a look at that. If f was the cutoff frequency, that's 0, isn't it? What's 1 over 0? Infinity. Now that would mean that the phase velocity in that guide would go to infinity at the cutoff frequency. Phase velocity is not the velocity of energy propagation. But the phase velocity is a mathematical construct. Let me try to explain this to you. You know how if you have a shoreline on an ocean, call this the shore, and I have a wave that's moving. Suppose my wave is this way and it's moving this way on the shore. Then if you look at the actual intersection of the wave's peak, I'm just trying to show you the peak magnitude of an ocean wave. On the shoreline, it would be the same as this would be the phase. The phase velocity And the movement of that point, which is called the phase, right there would be the same. Do you all see that? Just imagine, if a wave's moving this way, that intersection point is moving at the same velocity, correct? All right. Now, what happens if the ocean wave is moving this way with velocity v, and this is the crest? Well, this point right there is the actual phase velocity of that ocean wave on the shoreline as it breaks. That's gonna move faster, isn't it? Just imagine. Can you all see it? Right? What happens is this thing approaches this. Well, now, if this is moving in V phase, this one's moving a whole lot faster. Can you all see that? Just move at a small distance. And as this thing comes in normally incident to the shore, the velocity of this thing is approaching infinity. Can you imagine that in your heads? Now this point right here, where the phase intersects the shoreline, is the phase velocity of that wave on the shore, if you can appreciate that, all right? That's an ocean wave. With electromagnetics, when you have these tubes that confine electromagnetic energy, and you got light waves bouncing back and forth, that's what you have is this. Basically, they're ricocheting off the top and bottom. Well, what happens is, if you think about these things at the planar front of the waveform being like an ocean wave, as it's hitting the top, right, there's an imaginary point of equal phase, and it's moving at a certain velocity, right? Now what happens if you get really high frequencies, then the actual propagation is just in that direction, and the phase velocity is the velocity of the actual energy, or the peak. But as you get lower and lower frequencies, the waves are banging more and more vertically off. And at cutoff, which you're actually getting a waveguide, if you assume that the wave's propagating like that, at cutoff, the wave just is ricocheting up and back. So the apparent intersection of the phase front, if you can think of it the way I tried to do it with an ocean wave, it's going to infinity, but the actual velocity of energy flow goes to zero. Y'all follow me on that, class? So at cutoff, there's nothing propagating. Even though the phase velocity goes to zero, the velocity of energy propagation, or the group velocity, the phase velocity goes to infinity, but group velocity goes to zero. So remember, this is phase velocity.
Yeah, so basically the phase velocity is the speed, or just how fast the wave itself is moving inside the waveguide, but not how
No, it's
fast
the intersection point. The phase itself, this is a mathematical construct. Nothing is moving that fast. There's a point where there's an intersection of a wave front in the top or bottom of the guide. That imaginary point is moving at the phase velocity. Now, the actual velocity of energy flow, which is important, this is phase velocity. Velocity of energy flow, either V group or V sub E, that's equal to really 1 over just mu epsilon times the actual, matter of fact, let me do it this way. The velocity of energy propagation will be 1 over the square root of mu epsilon, and it's going to be times K. That's energy flow. It's inversely proportional to phase velocity. That's the velocity in the start of this one. This is velocity of energy flow in the waveguide. And that's the one that's important. This is misleading to me, because you think phase velocity is going to infinity. Wow, we can propagate energy, we can get information instantly. You can't. Right, you just can't. That has to do with, it's a mathematical construct, because it's the phase front's intersection point with the actual surfaces. That little point's moving that fast, but it's just a mathematical construct. This is the energy velocity, and that's the important one. All right, let's see. Talk more about that. Now I'm going to get to TE mode. It's a lot to swallow in one lecture, but we've got to do it. And this stuff, I'm just going to tell you, there's a lot of things that become apparent not so much from the mathematics, but once you start working problems, you'll see the really important things that have to do with rectangular waveguides, important factors. So that's all TM. TM mode, by the way, unfortunately is the easy one to understand, if you can believe that, compared to TE, but it's not used. Almost never, just to tell you that. The mode that is used is called TE. This is TE mode propagation. Now, when I talk about TE mode, what does it mean? Well, it means that EZ is now 0 in the direction of propagation. And remember when I started talking about this stuff, I said that if you have a waveguide, if we just look at the two plates, and you got waves bouncing this way, they go this way, and bounce down, and bounce back. Basically, you have a superposition of two wave fronts. We could prove this, but I mean, inside a waveguide. So, we talked about TM polarization. And I said, for TM polarization, there's no magnetic field in the direction of propagation, right? So, it meant this. It meant that the magnetic field, if this blue marker is the magnetic field, is out. So, I've got waves, I have E cross H, that are basically doing this. The magnetic field is out of the board. There's nothing in the direction of propagation. And this would be the Z direction. Now, when we have transverse electric, it's the opposite. Now it says the electric field is perpendicular, right, to the direction of propagation, Z direction. And the magnetic field is actually going to have a Z component. So now I got this going on. Can you all imagine that, class? E field's got to be perpendicular. This is the way the wave bangs around. So if it's going this way, right? E cross H, it means the H field would be this way. You all see, and the H field has a Z component. Can you all imagine that? That hit in the morning, it's 9 now. It's never easy, but you're going to have to go with. So for TE mode, transverse electric, EZ is 0, but we do have an HZ. So now we go down, and I could start with Maxwell's equations. But now I end up with this equation. I get del squared of HZ plus omega squared mu epsilon HZ equals 0. I'm trying to get this in this lecture, and if I had to start with Maxwell's equations, I would. We get the exact parallel to the equation we had for EZ, only with HZ. Right? Because there is an HZ component, but there is no EZ component. And a lot of this stuff is like, why did you? I mean, who cares? Well, HZ or EZ are the key things to actually solve it for velocity and everything like that. Those are the components of the solutions that really nail things down. If I solve the wave equation for EX or EY, there's too many unknowns. But here I've got HZ, there is no EZ component, thank God. And when I do this, I do the same thing I did before. I assume a solution. I'm going to assume, that separation of variables is possible, and it is. So I'm going to assume that HZ now can be separated as some function just of X, some function just of Y, some function just of Z, just like I did before. I go down there and I do the differential equation, del squared, and I'll go just put it in here that I have del squared of HZ with respect to X squared plus second derivative of HZ with respect to Y squared plus second derivative of HZ with respect to Z squared plus, and then it's going to be omega squared mu epsilon times HZ equals 0. This is where I was before with EZ, if you remember. And now I plug that in there, and then I'll divide by X, Y, and Z, so I'll just tell you what you end up getting. You're going to have X double prime over capital X plus Y double prime over capital Y plus Z double prime over capital Z plus omega squared mu epsilon times X, Y, Z equals 0. Or pardon, this is not X, Y, Z, that's, I already got rid of that. But I get this equation. That omega squared mu epsilon is beta unguided. And now the only way, again, for this to work is if this is a constant, and that is minus beta x squared. This is a constant, minus beta y squared. This is a constant, minus beta z squared. and this is just beta unguided squared. So, now, keep going on. I know I'm out of time, but I just want to do this. When all this said and done, and I get this second derivative of x with respect to x squared plus beta x squared times x equals 0. We know the possible solutions are going to be either sines, cosines, or exponentials. It's a second order homogeneous linear differential equation. But in this case, for the boundaries to work, and I'm going to stop here, x itself will have to be the cosine form of it. We'll talk about the reason for that in a second, or next class, but can't be a sine, and the reason is the actual derivatives of the h field in the z direction with respect to either the x or y direction at the surface. When when x equals 0, or y equals 0, or x equals a or y equals b have to be 0. The derivatives, which mean the derivative of that. I'll stop there because this next part is going to take a while to develop. I'm going to give you some homework. Let's do the homework. Did you have anybody have any questions about the problem?
For number 2, was there supposed to be a frequency given?
If you need to go, go. I'm just going to do office hours here because I got the whole class. You can go if you need to go.
Also, do we have a quiz on Monday?
No, I got to get through this
Okay.
team mode, so we'll do it Wednesday for sure, all right?
Okay.
But I don't want to do this. You can go if you need to. Consider this like an office hour, because I got it all here. There's no class. If you need to go, go. All right, tell me the problem again.
So, it's a TE wave having a magnitude of 6 volts per meter.
Hold on. Let me start here. You need to take a break, go ahead, but, and I hope, you mind this off? This is better in my office, trust me. I got a board, a big board. My office is small. Okay. You can keep the recording going.
Yeah.
It's still going.
Okay,
Yeah.
I want to make sure, all right. Ready, go ahead.
So
TE wave?
a TE wave having a magnitude of 6 volts per meter is incident from region 1 to region 2. The wave is incident at 60 degrees, and region 1 is free space, and region 2.
So this is free space.
And region 2 is a non-magnetic and lossless.
Epsilon relative 9, something like that.
Yeah, relative permittivity of 9.
All right, so you got an incident angle equal to 60 degrees?
Yes.
All right, now, we're gonna get, first off, I'm gonna get this angle of transmission, all right? I'm gonna get that angle, and then I'm gonna get this angle as well. Well, this angle's gotta be 60 degrees, doesn't it? Angle of incidence angle. How do we get that angle? Do you remember?
Beta 1
Snell's.
is 9.
We use Snell's law. Snell's law saves our lives all the time. So it's beta 1 times the sine of theta incident, right? Equals beta 2 sine of theta transmitted, right? Now, what is beta? Well, beta is omega times square root of mu epsilon, right? Sine of theta incident is equal to omega square root of mu epsilon for region 2, sine of theta transmitted, right? I'm just restating it, but now I'm putting in terms, beta in terms of omega, right? Y'all with me? Okay. Here's why you don't do frequency. Take a look there. What do you notice happening to omega?
Yeah, the omegas cancel.
Ah, thank God. Now, it's non-magnetic, right? So I can divide mu naught out of both of these, get rid of mu naught. Now I have this, right? First one is free space. What's epsilon relative for free space? Epsilon is epsilon naught, but epsilon relative is 1. Right? I'm getting rid of epsilon naught. That's 1, right? This is square root of epsilon relative in region 2. Epsilon relative in region 2 is?
9.
Square root is?
3.
3. Right? You're going to do this one. Sine of 60 degrees, let's see. That's 1/2, isn't it?
Yeah.
Sine of 60 is 1/2. So I have 1/2 divided by 3. Right? is equal to the sine of theta transmitted, or theta transmitted is a sine, inverse sine of 1/6. Can you give that to me in degrees, anyone?
Yeah, it's 16.7.
Okay, got that, right? It's a TE mode, right?
Yes.
For transverse electric, when you take a look at that, what is they want the reflection coefficient or what?
Well, it gave a list of things, and the first problem was the beta for 1 and 2.
All right.
So I did everything else.
Y'all see how you, I mean, for beta, what is beta over here gonna be? Wait a second. I don't give a frequency?
No.
Well,
So you can solve for everything except for the
The
beta
betas.
1 and 2.
beta.
Yes.
Well, yeah, I should.
And that beta, that beta 2 is gonna change the, propagation for this region 2.
I'll show you why. I mean, see this angle right here?
Mhm.
The only thing that's gonna happen, I'm gonna write this down here, when I take a look, there's gonna be 2 coefficients we need. We already know the angle it's coming off at, right? I mean, the transmission angle, right? We know all the angles. Now, if you take a look at that, I need reflection and transmission coefficients, right? For the electric field. So the reflection coefficient for a TE mode is what? A to 2, right? Times cosine of theta incident minus A to 1 cosine theta transmitted over A to 2 cosine theta incident plus A to 1 cosine theta transmitted, right? All right, you all agree with this? I'm gonna show you some tricks in this here. Now, eta in general can be rendered as eta naught square root of mu over epsilon. Do you agree with me there? So what I'm gonna do, and you don't have to, you can just follow me on this. I'm gonna replace all these etas with this, only I'm gonna use the proper values. And if you think about it, eta in region 1 is just eta naught. Eta in region 2 is gonna be eta naught over 3, isn't it? Y'all follow me? Because mu naught over epsilon, or epsilon in region 2 is 9, so square root of, the relative is 9, so square root of that is 3. Now, if you look at this, go back to this equation, I got, y'all notice on every one, eta 2, eta 1, eta 2, and eta 1, every one of them has eta naught in it, right? So I'm just gonna ignore that. I'm gonna divide through by it. And I'm only gonna put 1 for eta 1. And then 1/3 for eta 2. Okay. Now, after that, we got the transmission angle, right? We got the incident angle. Cosine of 60 is, let's see, cosine of 60 is
0.86, I think.
sine 60 is 0.86.
Oh, it's 0.5.
Wait. Yeah, that's right. All right, so why don't you just tell me what this is? It's negative, but I don't know how negative. Let's see.
I also found an example in the book that was a lot like this, but I was getting discrepancies between my etas and theirs in the book.
Well,
Or my
reflection.
Reflection, yeah.
Just tell me what this is.
Okay.
It should work. It has to work, right? Incident angle 60, so you got 1/6, the first one, 1/6. This should be the reflection coefficient here for the TE mode. It should be 1/6 minus the cosine of the transmitted. That one I don't know, but 1/6 plus cosine of theta transmitted. It's gotta be negative.
Yeah, I'm getting negative 0.703.
Anybody else? No. that's right. All right, what's the transmission coefficient gonna be? Remember, this is TE mode.
1 plus that.
Right. 1 plus minus 0.703.
297.
0.297. Okay, did I give you the answers to this?
Not for number 2.
All right. Yeah, and this is what I wanted people to work. I used to collect this one. All right, so, I agree that that's right and that's right if you did your calculation there. Now, what did they ask for? Go ahead, go through it all.
So they asked for the E field reflected, the
Okay.
E field transmitted, and then all three factors.
All right, first, I'm going to try to do this. You've got to get the direction, but unit vector and direction of propagation, you have to get that. But really for this, I know a unit vector and direction of propagation for the incident wave is just going to be, think about it. It's going to be the cosine is 60 degrees times AZ plus the sine is 60 degrees AX. Well, the sine of 60 degrees is, I think it's 866 is a close approximation, AX, and then it's gonna be plus 0.5 AZ. Y'all agree with that? It's positive. Now, for this one, the reflection coefficient, or the unit vector in the direction of reflection here is gonna be same AX, 0.866 AX, but it's gonna be minus 0.5 AZ because it's going in the opposite direction. Y'all follow me? All right, now a unit vector in the direction of propagation here, if you think about it, is going to be what? This is going to be simply the AP for the transmitted is going to be sine of the transmission angle, right? AX plus cosine of transmission angle AZ. Can you tell me what the sine of the transmission angle there is?
0.288.
0.28?
0.288, which is 29.
And what's the cosine?
0.95.
Okay. Now we got that done. So, next. Now again, I didn't give you a frequency.
Also, it does give you that the incident E field is 6e to the minus j 1.84x
Yeah.
plus 1.047.
You know, hold on, we got E field incident equal to 6e to the minus, say it again?
Minus j, parentheses, 1.814x plus 1.047 z in the y direction.
You know what, we can get beta. You know how come? When I look at this, what is this right here? This is beta in region 1 times the cosine of the incident angle, right? What is this? That's beta in region 1 times the sine. So if I take this and square it, I get beta 1 cosine squared of incident angle plus beta 1 squared sine of the incident angle. Sine plus cosine is squared is equal to, sine squared plus cosine squared is 1. What I'm really saying is that beta in region 1 will be equal to the square root of, you can give this to me, now we have beta in region 1, 1.814 squared, I don't need to give you a frequency, plus 1.047 squared. And can anybody give that to me? Two can ask me about this.
2.094.
What is it?
2.094.
Is that right, guys?
I found it a different way. I just divided it. I did the same thing you did, but I just divided by whatever I got for cosine of 60. I just divided.
Yeah, you can do it
1.814
that
by
way too. But this is the way it's standardly done. If you look there, you just square both terms, take the square root to get the value of beta. Now that's beta in region 1. So what's beta in region 2? Well, beta in region 2 is omega times square root u naught epsilon naught, right? Times square root of mu relative epsilon relative in region 2. Well, this is beta 1, so beta 2 is beta one, right? And it's really gonna be times square root of epsilon relative one in this case, which is square root of 9 is 3, so beta 2 is 3 times 2.094. You can check with me. I don't know, can you give me a number for that one?
6.28,
6.28?
yes.
Okay, got that. Now for the E-fields, I'm gonna come over here. I'm assuming you guys written this down. This problem is about bookkeeping more than anything. But it is making you aware of, you have to have some grasp on how to get these, of the mathematics involved in getting them. And knowing that the argument's here, this is beta 1 times the sine of the incident angle plus beta 2 times cosine of the incident angle times z. It'll give you everything. So they want the transmitted E field?
Yes.
Okay, we can get everything, but we'll start with the transmitted E field, because that's the interesting one. So transmitted E field, right, will have the form E naught transmitted times E, this is for the T mode, minus J beta 2 times sine of theta transmitted X plus cosine theta transmitted Y, Z, right, in the AY direction, right? All right. E dot transmitted is simply what? Transmission coefficient times E naught incident, whatever that is. Then we're gonna have E to the minus J beta 2, we got right here, right? 6.28. And then, you can, because this is where this is kind of nice right here. For the univector direction transmission, this is right there, the 0.288 is the actual sine of the angle. So I can put that in here. 0.288 x plus 0.95 plus 0.95 times z, right? Y. Now you can do the math on this one, but what does that render for the transmission? We got the transmission coefficient, it's 0.2 something,
297,
times 6, whatever that is.
1.782.
1.72?
1.782.
782, e to the minus, if you want, you can multiply it out, but you don't have to. 6.28 times 0.288.
1.8,
1.8?
yeah.
1.8 x plus 6, huh?
5.966.
AY. All right, that specifies the transmitted field, the E field. How do you get the transmitted H field? Yeah, but ultimately for this one, we're gonna have two components of the H field, right? All right. Now, it's in his book, isn't it, class? He does that. I don't know if I need to do this, but you know, in his book, he has, this is the E field that's transmitted. To get the H field transmitted, we can do it this way. It's gonna be what? 1/8 in region 2, right? Which is 8 in region 1 divided by, or it's 120 pi divided by 3. So that's 40 pi, right? So we can get it this way, 40 pi. And then it's gonna be unit vector and direction of propagation, which is that. And it's crossed into the E field transmitter, which is right there. I'm just gonna cross into E transmitter, AY. Now, y'all see that really what we're doing here when we do this, we're gonna take 1/40 pi and we multiply it by 2.288, and we have AX crossed AY gives you the AZ component. And then it's just gonna be the same deal, 1/40 pi times 0.95 AZ cross AY is minus AX, and you have the two components of the transmitted H field. Do y'all follow me on that? Now, we'll have the same exponential argument up here. This is gonna take, I think you can handle it. You okay with that part? How do you get the reflective electric field? It's a reflection coefficient, right? Times E naught incident. Y'all agree with that? Right? And we have the reflection coefficient's negative, isn't it? Right? But whatever it is, we've got it. Now we can get that, and then we're just gonna put one. E to the minus J, and I can tell you, if I gave you this right here as the incident field, I simply take that argument, the only thing I do is right there I put a negative sign, because now it's going in the other direction. So it's E to the minus J, and what's the first value there? 1.814 X, and then it's gonna be minus, what's the second value?
1.047.
Times Z, and that would be the AY direction. I don't know what that is, but you can take 6 times whatever the reflection coefficient is and get it. All with me? You can get the H field the same way. Is there anything else about this besides the field quantities? We did get beta in region 1, beta in region 2, without a frequency. But we could, how would you get the frequency? Good question.
You saw it from the
Yeah, sure.
After you find it.
After, since I know this is beta in region 1, right? That has to be equal to omega, which is 2 pi f times the square root of mu epsilon, right? Well, the square root of mu epsilon is 1 over c. So you can just take c times that and divide by 2 pi, and you have the frequency. How would you get wavelength? I'm just asking these things. I know I'm tired too. Huh? 2 pi over, yeah, that would be wavelength, right? So we can check the boxes on that. And if I give you any problems on oblique incidence for a quiz on Wednesday, I would give you the equations for the general field equations, all right? I'll give you the reflection and transmission coefficients. You know, there's equations that are a little tedious to remember. I would give you them, and really, when I talk about this stuff, the only thing I really care about is transmission angle, reflection angle, which we can get, obviously, and the actual values of the magnitude. I don't expect you to write exact equations, but I'll always ask what's the magnitude of the transmitted H field, the magnitude of the transmitted E field, or vice versa, the magnitude of the reflected E field, and stuff like this. But I don't ever worry about you rewriting those equations, because that's tedious. And most people couldn't do it from memory, unless you're really immersed in it. Okay, other questions?
So I kind of have a question about that. So, for example, if it said the magnitude of the transmitted H field for this.
All right, now here's how you get it. You ready? Magnitude of the transmitted H field. I got the transmitted E field, right? Once the E field is transmitted, I know that the E field transmitted over the magnitude of the H field transmitted. Now that's both components. It's the square root of the x squared and the z squared component of the H, the square root of that. That's going to be equal to just eta in region 2. The ratio of E to H for any propagating wave in free space, after it goes through that barrier, is always going to be just simply equal to eta in that region, which is
45.
right, it's simply square root of mu over epsilon in the region, and it'd be 125 over the 3 or 40 pi. Y'all with me? So you can get, that's how you get this. You get the magnitude of the E field, then divide that by eta in region 2 to get the magnitude of the H field. And similarly, if this was a TM mode, then once you had the magnitude of the E field in either of the regions, to get the H field, the magnitude of the H field, you're going to do the same thing again. Okay.
So you would have to do all of the crossing and everything.
We just throw out the e to the negative j omega.
What's that?
We just throw out everything.
Yeah, because magnitude is the way, in the real world, that's what they care about. What they want to do is they want to know the value of the peak of the electric field that's transmitted into a region, or power, right? But they don't care about that equation. That's a mathematical construct that helps us solve these things. Other things, other questions? Yeah, I've been talking a long time. Well, coming up on 2 hours. 20 minutes short of 2 hours, what else?
That's it for me.
Did y'all do those? I know you did them. You did them, obviously.
All of them with that one.
Right, well, I hope it made sense what I just said, and I want to tell you about this lecture today. It is a bit tedious to go through that, right? But you'll start appreciating once you get the problems, because they're not that bad. The real thing about this with waveguides, you always worry about the lowest order cutoff mode, which is the TE mode, by the way, not the TM. It's the 1.0 mode. Then after that, if I give you a frequency that's being operated, then you calculate the impedance, and I'll show you how we actually take these waveguides and we reduce them to the equivalent transmission line. You know where the transmission line things you worry about are what? The impedance, characteristic impedance, and you worried about what the wavelength is along the transmission line. Because once you know those two things, you put any load on there, you can figure out the input impedance, but I'll have to do that another time. You know, 8 o'clock is not my favorite time. When that alarm went off, that clock is not my friend. I don't know if anybody's ever broken an alarm clock. Today I came close.